One reaction that we use it a lot actually to figure whether we have a ketone that it is attached to methyl group is a hollow form reaction. Hollow form reaction is one of the rare reactions that's that you can actually use it to oxidize ketone. Remember, any method I practiced until now, I said if you reach ketone, it's kind of like the dead point. Ketone is not going to get oxidized anymore, stay as it is. But there is a method for it and to oxidize it. A problem with ketone is attached to two alkyl group. And we know R minus is not a good leaving group. You need to make R stable enough, and then it will leave the carbonyl group. But one alkyl group alone is not stable, and because it's not stable, and you can easily break this chemical bond. And this is the reason we say getting ketone is kind of like a dead point. Okay, let's go after this one now. The hollow form reaction, the way it's going to happen, it will it's going to happen in a basic solution, and entire reaction is going to happen on alpha carbon. So first step that you're going to do, you will find the alpha carbon. The alpha carbon is the carbon that is adjacent to the carbonyl group. Now, if the alpha carbon happen to have like a hydrogen there, then you can actually take those hydrogen and replace them by by say halide or anything else. How I can run nucleophilic reaction. Okay, so I'm running technically I'm running a nucleophilic reaction with sodium hydroxide, and because the solution is basic, if you just simply add strong base like OH to the carbonyl group, you will get a negative charge there, but nothing is going to happen to it. Okay, and because the solution is going to be basic, and like you will get a negative charge, and so stay as it is. And but there is another way, like for the reaction to move on, is to take one acidic H, and it's going to go after this H, and we'll take that H out of the system. Now that we get this species, this one will have a negative charge, and we have R here. We can have a resonance. This negative charge, it will be shared with carbon, and that carbon is going to give the pi bond to oxygen, and it will give us an enolate. And now we move the negative charge from carbon to oxygen. So through resonance, we managed to stabilize it. But this one also, it can go back, and it's going to create a negative charge on carbon. That carbon is going to be a strong nucleophile, and if you expose it to any halide, it will react with it. So now I'm gonna next step after generating this technically enolate, I'm gonna react it with an halide, like say X2. It can be chloride, bromide, or iodide. And if that one happen, I will have X attached to carbon, and of course I get also salt. Okay, sodium, it will be paired with another, like the halide, and it will give us the salt. Now, it depends how many hydrogen I have on this carbon. I can keep running this reaction and more and more. Now, if you happen that you have another hydrogen there, you can actually run the same reaction. So whenever you got the first, technically a product, you will have another reaction, the base, and the base is going to be sodium hydroxide. So you are using excess from this one to attack hydrogen, and then again we get a negative charge, and this negative charge is similar to this intermediate. It can get stabilized, and you share the lone pair with carbon, and then carbon is going to give pi bond to oxygen. It will put a negative charge on oxygen, and so that's species. That way it will get stable. And now I will expose it to another mole from X2, and now I got two halide attached to carbon. What's the purpose of this? I know CH3 with a negative charge is not good leaving group. Why? Because it's going to be really, really unstable. But I know that electronegativity of, for example, chloride is way higher than electronegativity of carbon or hydrogen. Okay, or hydrogen. Okay, again, what's the point? The point is this: if you manage to replace the hydrogens by chloride, you can actually turn CCl3 to a good leaving group. Why? Because chlorine with high electronegativity, it will pull electron density from carbon, and it will stabilize the species. Now that is going to be a good leaving group, we can kick it out of the system and replace it, for example, by hydroxide. And if that one happens, we get acid. So until now, I have 2 mole from X attached to carbon, and next I'm going to add another, mole from, from the base. And this time I will take those 2, hydrogen, 3 of them technically, and I will replace them by, X. And that's going to give me, technically CX3 time. And now that I got this species, that can be a good living group. So if I want to summarize it, I added another mole of sodium hydroxide to this compound, and assume this one is hydrogen, not carbon. If it's a carbon, it will stop there. Okay, so this one is not going to move. It's not going to move forward unless you replace it by hydrogen. But for now, stay as it is. But if you use methyl, then of course you're going to have 3 hydrogens there, and 3 of them they will be replaced by the chloride, bromide, or iodide, and you can kick it out of the system and replace it by OH. Okay, So the overall reaction, it can be this. If you have alpha carbon and the alpha carbon happen to have 3 hydrogen on it, you can replace those 3 hydrogens by chloride, bromide, or iodide, and then kick it out of the system and replace it by sodium hydroxide. So the overall reaction is going to be this. I'm going to kick the methyl out of the system. So I'm going to say I have methyl, that's hydrogens replaced by bromide 3 times, okay, 3 times, and we're going to have a negative charge there. And now what happened with the position of the methyl, the alpha methyl? Alpha methyl, it will be replaced by OH, and that's going to give us an acid. And then, because the solution is basic at the beginning, it will be this. It will be, forgive me, it will be the carboxylate, but if you treat it with acid, then it will turn to OH. Now, how about this species, and this one? And whenever you add acid to the solution, because it's a base, very soon it's going to get H, and it will turn to this one. It will turn to HCBr3. Okay, I forgot to write the R. So we have this compound CHBr3. I'm going to erase that part. This new product. Now, if you use iodide instead of bromide, the compound is going to precipitate. And so if I use iodide instead of bromide, I get CHI3. That's going to be solid, and it's actually yellow color. And so if you see a solid yellow precipitation at the bottom of the flash, that's a good sign that your ketone, it has a methyl substituent. Okay, it's very common actually test for ketones. And we have a good number of examples. And so one of the examples that like I already practiced, I said this one is simply is going to turn to this acid. I'm not going to go through the mechanism again, plus CHBr3. Okay. And but let's practice more example. And so I'm going to find the alpha carbons, and I have 2 alpha carbons, and that's second alpha carbon. And this one, it has 1 hydrogen, that one hydrogen, but I said I need to have 3 hydrogens. Which carbon has the 3 hydrogens? That carbon. So you're gonna kick those methyl out of the system, and they will leave the system as a CHCl 3 times, plus, now instead of methyl, just simply write OH there, and that's gonna be the final product. So the final product, it will be this molecule. Simply put OH instead of the methyl, and that's your carboxylic acid. And the second one is going to give us this molecule. So this acid plus, of course, we're going to get the CHI3. And so as you see, I replaced the chloride by iodide. And in order to show you that, I can use either of those halogen to run the haloform reaction. And this one is going to be solid, so that's going to be a positive. Technically, it will give you a positive result on for the iodide reaction. Okay, now I'm going to highlight again. I'm going to highlight the alpha carbons. I have 2 alpha carbons, and I want to see whether there is a hydrogen there or not. And on this alpha carbon, I have only 1 hydrogen. And how about this one? I have 0. Okay, and so I'm going to call this 1. That's 2. And in this case, because I don't have enough hydrogen, only thing that is going to happen is technically you can get rid of the hydrogen and replace it by iodide. That's possible, but then nothing is going to happen after this one. This one stay as it is because it doesn't have any methyl attached, any hydrogen attached to that tertiary group. And how about the second one? The second one, we have two hydrogens on those two alpha carbon. I'm going to call them alpha. They are identical. And I have another alpha. This is alpha 2. It has also two hydrogen. And you might say, because we have only two hydrogen instead of three hydrogen, the reaction is not going to move and nothing is going to happen. Okay, let's test it. The purpose of having three hydrogen is to put enough electron withdrawing group so it will be a good leaving group. So I want to turn CH3 to a good leaving group. And that's the reason I said I need to have three hydrogen. But we have a carbonyl group, and those carbonyl group, they have sp2 hybridization, and I have two of them. So what will happen if I get this, let's say, get this molecule? So first step, imagine you did this. You replace this two by chloride. And now the carbon that I'm going to highlight, this carbon is going to feel a huge, electron withdrawing, effect, or, like a pulling effect from neighbor. Those neighbor going to pull electron density to their side. And so it means if we can, break any of these bonds, the system is going to be stable enough. And in fact, yes, it's going to happen. And that's going to give you such a species. So I'm going to break one side. That's going to give me Cl2 with a negative charge. And here we have a carbonyl group. And what else? That side, okay, I have O, and I'm going to attack it here with hydroxide. So I will have OH there. So one of them got replaced by technically OH. I got the carboxylic group. Now, what will happen to this carbon, the one I'm going to highlight, what will happen to this one? Okay. That one, it can share the lone pair with the carbonyl group. And because it can share it with the carbonyl group, it's going to be stable. Okay. Now, is there any chance to have a chemical reaction with, chloride? And yes, it can happen. And if that one happened, then you get such a species. So until now, we have carboxylic group there. And here we have a carbonyl. This carbon is going to react with another mole from Cl2. And now we will have 3 chlorides. Okay, so from 2, I turn it to 3. Okay, highlight this one. Now I have 3. And next step, I'm going to add OH to it. If I add OH to it, this one is going to turn to another carboxylic acid, another carboxylic functional group. So I got 2 of them. And plus 1 mole from CHCl 3 times. So it's possible to oxidize the ketone molecule, the diketone here. Why? Because those diketones, they will make the hydrogen atom too acidic. And now we can take the hydrogen atoms and replace them by 2 chloride. And now that we have CCl2, that neighbor to 2 carbonyl, it's possible to break any of this, technically chemical bond, this chemical bond, either that one or that one. And because we can have resonance between the negative charge and the carbonyl, it will be stable enough. And now that it's stable enough, we can react it with chloride and, technically get the third chloride there. Now that we have the third chloride, this one is going to be a good living group, and we can kick it out of the system by a base. And I should write this one. Now, this is going to be first step, and that's going to be the last thing that you will add at the end of the reaction. You will treat it with acidic solution in order to turn the carboxylate to carboxylic groups. And this is going to be end of this lecture, and thank you very much.